into here. Let me just make sure. Yes, we are live. Hello, everyone. Thank you for joining us today. My name is Jeffrey, and I will be your host for today's webinar. We're going to be extending the boundaries of the RF spectrum processing with Mercury RFS1140 RFSiP. So we've got a lot of great content here for you today. Good presentations from AMD, Jariet, and Mercury. So I want to make sure that we give plenty of time. So I'm going to run through our housekeeping really quick, and then we will get going. So on your right, you will see a question box. If you have any questions, go ahead and drop those in the box over there, and we will do our best to get to you at the end of the webinar. Right under that box, you will see a survey. If you could fill that out before you leave here, that would be super helpful as we try to bring you the best webinars that we can. And then right above those two modules, you will see a resources tab. In there is a few links, so you can check out the product that we're going to be talking about today, to learn a little bit more about Jariet. And if you want to reach out to AMD sales, you can do that in there as well. And next to the links tab, you will see a documents tab, and in there is a PDF copy of today's slides, so you'll be able to follow along or use those for references going forward. And you will be able to come back and watch this on demand anytime. You can use the same link that brought you here, and we'll also be sending a thank you link shortly after we close here today. All right, with that housekeeping, I am going to introduce today's speakers. First, we have Dagan White from AMD. He is a senior product marketing manager with our aerospace and defense team. Following Dagan, we'll have Philip Pratt. He is the Vice President of Marketing at Jariet Technologies. And then following that, we will have a deep dive with Michael Potter from Mercury. He is a firmware and FPGA developer. So I don't want to waste any more time. So I'm going to go ahead and throw the ball over to Dagan to begin the presentation. Dagan, go ahead and take it away.
Okay, great. Thank you. Hi, everyone. Okay, great. Thank you. Hi, everyone. Thanks for joining today. I'm here to talk to you about our Versal offering, and particularly a little bit of background around our aerospace and defense business. And that'll lead into the RF System-in-Package, where we will have coverage with Jerry will talk about the data converters, and then Mercury will talk about the RF System-in-Package all together. So within aerospace and defense at AMD, our heritage comes from the Xilinx side, and we are now AMD embedded business unit that focuses on aerospace and defense. And with that, we bring over 30 years of heritage in this domain. We cover pretty much every type of system from land, air, sea, space applications. We have system architects that cover avionics and missile munitions, as well as electronic warfare, ISR, EW. And then on the software-defined radio and SATCOM, we have another architect and a space architect as well. So we have architects that cover each of these domains. And on this slide is just a little bit of highlight about key careabouts and key factors that we address in these domains. But certainly it goes beyond that. And you can learn more at www.amd.com/defense. And that'll take you to that website where you can learn more. Okay. So if we look at our product offering, as mentioned, our background, it was the Xilinx side was really an FPGA company, but over the years since 2011 through today, we've really grown into an adaptive SoC supplier. And not shown on this slide is the fact that as part of AMD, we have recently acquired the embedded x86 business, which we will be ramping up as well. But this slide here is covering specifically the progression of our products from FPGA through the adaptive SoCs that we have in Versal today. And within Versal, there's several subfamilies. AI Core is the first subfamily that was launched, as well as the Prime. And the AI Core product is the one that we will be talking about in the RF System-in-Package. So it's a Versal AI Core VC1902, which is the largest AI Core device with AI Engine 1. So that was our first product that we brought out, like I mentioned, with this architecture. And I'll cover a little bit more about that. But before I do, we did also recently launch the Versal Edge and Prime Gen 2, as well as a Premium Gen 2 product. And these are really Versal extensions. And our Versal RF product line was also launched in this time frame. And it has some features of the Versal extensions, but it's actually included in the base here on this slide. So those are new products also to consider as you're looking at our portfolio. Going forward, we will be building on a multi-node kind of platform. We are continuing to add 16 nanometer UltraScale Plus devices, as well as more 7 nanometer, while we're bringing online next generation process nodes, which will be chiplet based and integrating various technology nodes in the same package. So if we step back here and we look at the Versal architecture in general, what you see in the middle of this pictorial here is the programmable logic, and that was kind of the classic FPGA. And if you might be familiar with our Zinc products in 7 series and in UltraScale Plus, we had the Zinc UltraScale Plus MPSoC. We added in ARM processing subsystems, which were comprised of ARM Cortex application cores, as well as ARM Cortex real-time cores. And now in the Versal, we have the application processors, dual A72, and the real-time core is a dual R5. So these are like a basic system level control, functionality kind of processor integrated with the programmable logic. We also added a new feature in Versal, which was AI Engine technology. And I'll talk a little bit more about that down further in the presentation. But these AI engines it's a processor array of VLIW processors that can be used for signal processing and machine learning. So those core capabilities are connected through a network on a chip to system, kind of high bandwidth system level interfaces, including DDR controllers, multi-gigabit Ethernet, PCIe Express, and so forth. So that's kind of the root of the architecture of the Versal product. And everything really seen here is included in the Versal AI Core VC1902. Up to, we have 32 gig SerDes, and we go up to 100 gig Ethernet. We don't do the 600 gig Ethernet. We don't do the HBM. The RF will be brought in here in this particular case with the RF System-in-Package. And then separately, we do have a Versal RF product line. Okay. So if we look at the AI engine, which is a very unique processing element in the Versal architecture. Like I said, this was introduced with the AI Core series. It's software programmable. It can run up to 1 gigahertz in the lowest speed grade, and you can run massively parallel computation in these AI engines. In the VC1902, there's 400 of the AI engines. We do have a range of AI engine count depending on which device density you're in. But there's a significant bandwidth interface between the programmable logic and the AI engines. From there, if we look at AI engine support, we do have a signal processing library, a DSP library for this. It ties in with the DSP library for the programmable logic as well, which supports the DSP58s. The AI engine DSP library supports multiple variants of the AI engine. VC1902 is the AI engine 1 architecture. However, we did introduce a an AIE ML and an MLv2 in the Edge and the Edge Gen 2 products. The same DSP library can be functions can be ported across. If you're using the library, you can port those functions across between AI Engine architecture. And it's an open source library that's accessible. It's C++ programmable, and it generates everything for you from that point. Now, when you're using AI engines, one thing about them is that the best possible capability in terms of processing compute performance is when you use AI engine, a shared mix of AI engine and the programmable logic for the computing. So we'll show something on that in a couple slides here. Looking at this DSP library, there are DSP filters, various transforms, some basic linear algebra, solving linear systems functions, as well as SIMD compute kernels. Like I said, this supports the different AI engine variants, for which AI Engine 1 is the one that's in the VC1902 in the RF System-in-Package. And we do support various data types, and that's a property that you can apply in the DSP function. So if we add new data types, you don't need to redo your whole architecture. We can modify that in the call to the DSP library. And these libraries support, it has full support in the AMD Vitis Model Composer. So collectively, that is the DSP library function. If we look at an example here, on the left side, this is showing resources, memory count, memory utilization, the latency, dynamic power of a programmable logic implementation versus one that is a combined AI engine and programmable logic implementation. And this is showing a case of a 32K point FFT running at 8 gigasample per second with CINT16 data type. So what you see in the leftmost case is you get the programmable logic utilization and the latency of 48 microseconds and power of about 9.6 watts for the dynamic power. When you run this with the AI engine, like I said, this is splitting this function across AI engine and programmable logic. A slightly different architecture is employed to get the best throughput out of the AI engine. And you can see the resource utilization there where the programmable logic is significantly reduced, dropping from 153K LUTs down to 8K LUTs, and from 171 DSPs down to 12 DSPs, as well as you can see the flip-flop utilization. And this is in exchange for adding in 50 AIEs, for which 16 are used for compute, and then some others are used for memory buffering and so forth. But in this case, the AI Engine PL gives you significantly improved latency. So it's 7.5 microseconds versus 48, and roughly 6.7 watts versus 9.6 watts in the purely PL case. So what this shows is that with AI Engine utilized for signal processing, you can significantly reduce latency and power. Which I think is an important factor when we're looking at this RF System-in-Package. And I guess I'll bring this up a little bit later before I hand it over to Mercury as well. So if we look at the Vitis solution stack, design entry is at a C++ level for the AI engines. The vector processor operations are utilizing API functions, or if needed, lower level processor intrinsics. And for the programmable logic, you can program in C++ using guidelines for pragmas to make efficient conversion to RTL. And rather than coding everything from scratch, we do have the Vitis accelerated libraries, which are open source, available in GitHub, and they include common functions. We also have some reference designs available that we've done. So the Vitis Core Development Kit provides the software development tool stack, such as the compilers, the cross compilers, to build the host program and the kernel code. and everything you would need. The Vitis runtime provides an API and the drivers for the host program to connect to the target platform. There are base platforms that we provide from AMD, either chip down or with an eval card, such as the VC, it's showing the VCK190 here or VEK280. But in addition, the Mercury RF System-in-Package, which we're talking about today, is also a target platform, and Mercury is providing a BSP and so forth for that, which you can target using these very same libraries and the Vitis tool flow. Okay, so if we look at the tool flow overall, at the lowest level is Vivado here, and Vivado is what is used to program the programmable logic in all of the kind of hard IP blocks. At the higher level, we have Vitis. So Vitis supports the embedded development. We have included in Vitis, we have the HLS, which converts, you can code in C, C++ for IP that targets the programmable logic. And we also have Vitis Model Composer, which is a MATLAB Simulink plugin for signal processing development. And then separately from Vitis is a tool that's called Vitis AI, and this is used to develop ML models that target either an overlay for the programmable logic or an NPU overlay for the AI engines. So it is possible to split the AI engine usage so that you can run a combination of signal processing and machine learning. And what we're seeing is increasing interest for machine learning in the RF signal processing pipeline. And this is an activity that we're actively working on within our aerospace and defense team. So if we look at the RF product landscape that we offer, we do have the Zynq UltraScale Plus RFSoC products, which you can see here extend up to close to 6 gigasample per second in the Gen 3 products, actually 5.4, and then in the DFE it goes up to close to 6. But with Versal RF, we brought in increased sample rates up to 32 gigasample per second. We have an option in AI RF family. It's Versal RF family that is it's either 32 gigasample per second or 8 gigasample per second, and the analog bandwidth of that product is 18 gigahertz. We do have some customers that want to go beyond that. Some applications require it for electronic warfare and some other areas. And so with that, we've partnered with Mercury Systems to develop this RF system-in-package using Jariet data converters connected into the VC1902. And that's what Jariet will be talking about, those data converters, and Mercury will talk more about the RF system-in-package in particular. But for bandwidth needs that go up to the K band and to the KA band, the Mercury RF system-in-package is the correct product to target. Or if you need wider bandwidth coverage, even down to lower end, but you still need that high end. So if we look at the Versal enabled RF system-in-package, what you get with this is you have integrated Jariet data converters in the package with the VC1902. This is a 47.5 millimeter package. It also includes some core memories, so the 1DDR and also the non-volatile memory to bring up the device. So with this DDR, that can support the processing system. There are other DDR controllers on the device that are brought out, so the customer user can use those on their circuit board to add in more memory for application level processing. There are some of the transceivers and so forth that are used up for the connectivity to the Jariet data converters in this case, but there are 12 converters left over that are supporting 300 gigabits per second worth of bandwidth for data offload. So the connectivity, as they'll go through, is through SerDes-based connectivity of the the data converters into the VC1902 device, and that uses JESD204C as the interface. But within that, if you're looking at this relative to some other implementations that exist on the market that are more chiplet-based integration, you might say there's added latency across the JESD interface. However, as we showed with the AI Engine DSP implementation, we can significantly reduce the latency of the processing in this device. And so overall, if you're evaluating this relative to some competitive devices, you would want to look at the full system level performance, including the bandwidth of the connectivity across the interface, as well as the signal processing. So with that, I will turn it over to Jariet and Mercury.
Hi, everyone, and thank you, Dagan. That was a good overview of the Versal and the Xilinx portfolio. I'm Philip Pratt, VP of Marketing with Jariet Technologies. I'm going to spend some time today introducing you to more details on the Electra product, which is embedded in the Mercury RFS1140 module. I'm going to talk about it in the context of it being a die, because obviously that's what's inside the module. We do, of course, also provide catalog package parts in BGA form. A lot of times people are kind of curious, what do these converters do? Where are they used? When you have this much bandwidth capability across this much of a wide frequency range, the answer really is we're used everywhere. With the common architecture, you can be applied across aerospace and defense markets, from radar systems, electronic warfare, satellite payloads, software-defined radio for communications. And there's a lot of flexibility with this frequency range to build a common piece of hardware that can be used across all those applications. So it's around the architecture is around a direct RF sampling architecture. By doing that, it enables a true software-defined radio capability with the small signal RF coming in and out to SerDes going in and out. The heart and soul of this is based on this simplified diagram, which shows how a high-speed DAC is directly generating RF signals, a high-speed ADC is directly taking them in. There is some digital up and down conversion to give the benefit there of reducing the data rates at the high-speed interface down to the level that's required for the instantaneous bandwidth of the current mission. And really where you can define the personality of the card with more intention to frequency bands would be in the gray box on the left, where you would potentially change out the RF front end based on, in one case, maybe an L band use case, and the next use case might be Ka band, all with a common RF transceiver IC capability. You see, we note there an RF range of 100 megahertz to 36 gigahertz. We actually work a little bit beyond that range. I'll cover that here in a moment. And then over on the baseband processing side, you can actually switch out the FPGA to different qualities and cost points, depending on how much SerDes and how fast the SerDes needs to be, which directly translates into how much instantaneous signal bandwidth you need at that moment. The specifics of the Electra device: the Electra-MA is the superset version of the product family. It's a 64 gigasample per second dual channel 10-bit A to D and DAC. Every one of those combinations of A to D and DAC is supported by its own clock synthesizer, a coarse and fine 4-channel digital down converter. There's a linear EQ filter for improving spectral linearity for the ADCs in band. There's an embedded capture and playback RAM. This can be used with a 64-point FFT engine on every receiver. It can also be used to generate simple waveforms, perhaps for system debug or calibration. There's independent NCOs for every digital down converter and every digital up converter. The dies and the chips support synchronization across multiple dies. The die is typically controlled with API firmware through an internal CPU that's embedded in every die. The digital up and down converter range as little as by 8 and as much as by 1024. This gives you a lot of flexibility to do anywhere from 6.4 gigahertz wide IBWs over to the FPGA, down to tens of megahertz over to the FPGA, depending on your sample rate. The power consumption of the die, which I'm going to go into more detail here in a moment, typically runs about 6 to 9 watts for the 2 channels of transmit and receive, running in full duplex across this sample rate range of 40 to 64 gigasamples per second. And the data interface over to the FPGA utilizes a 30 gigabit per second JESD 204B 204C interface to the FPGAs. There's a total with each die of 16 RF or SerDes transceivers. Now, within the context of the Mercury RFS1140 module, we have the combination of the AMD Versal VCU 1902 FPGA die, several micron memory bank die, and then 2 of the Jariet Electra die. So that gives the capability of that previous diagram times 2, providing a total of 4 transmitters, 4 receivers connected right to the Versal FPGA inside the RFS1140. Now, I wanted to introduce a couple of pieces of information today that might be new to you. So here's 3 fun things to learn about Electra. One would be a lot more detail than you'll find in the public domain previous to now over the power consumption over different modes. So as an example, on the left table, we have full duplex operation of each 2-channel die. You'll note of a configuration there on the left, 2T2R full FD for full duplex. That means the TX and the RX are on 100% of the time. I've given some examples at the top there at 64 gigasamples across different decimation and interpolation factors that are done on chip. You can see the power range there of about 7.9 to 8.8 watts. As you slow down to 58 gigasamples and 51 gigasamples, you see the power going down to the 8 and 7 watt range. I've given an example here at 40 gigasamples. That's the minimum rate that the sample rate can be generated inside the clock synthesizer of the Electra die. There, the power consumption is down to close to 6 or even below 6 watts. So about 3 watts per transceiver at that point. The device does, however, support an external clock mode where you can go below 40 gigasamples. The PLL is the limit to 40 gig with the internal clock synthesizer. But with an external high-frequency clock, you can go to frequencies or clock rates below 40 gig. Here I've given an example of just how well the power can scale with the Electra die. At 20 gigasamples per second, the power is below 4 watts. So that's less than 1 watts for a small signal transceiver in and out of the chip. The right side of the table is the half duplex, which took the simple case of assuming TX was on 50% of the time. During that time period, RX is in sleep mode, and vice versa when RX is on. And you can see here the power scaling from about 3 to 7 watts across this range. So it is a very power efficient chip that can scale well with different sample rates and configurations. Another aspect I wanted to reveal to you today is that even though we advertised the product from 0.1 to 36 gigahertz, I think some of that just came from the simplicity of the availability on the balance on the characterization equipment we were using. Because as you may know, it's very difficult to find a singular balun that can convert single to differential or differential to single-ended across this entire frequency range. So we thought we'd at least let people know that the part does in fact work pretty well below 100 megahertz if there's a use case for that. Here's the low frequency cutoff example here from the simulation of the input drive of the ADCs for Electra. You can see the device is really quite usable down to 10 megahertz and perhaps below that as well. And a couple other modes that I wanted to explain that aren't really that transparent when you first look at the Electra. Inside every ADC DAC transceiver, there are different loopback modes embedded in the die. So from RX to TX, you actually can go from the ADC data out to the DAC data in, up to the full sample rate of 64 gigasamples per second. So that's going to allow a loopback of the data you're simultaneously capturing going right back out the transmitter at a very low latency. You can also go from the digital down converter output back to the DUC output or input. This is after the DDC function. You can also loop back from the JESD 204 internal layer right before the driver is coming on and off the chip. On the transmit path, we could go from the transmit DAC back into the ADC on chip up to 36 gigahertz. And then we can also loop back from the duct output to the DDC input. And lastly, you can verify your SerDes connectivity with a simple physical layer test SerDes loopback. All of these functions can be used for general debug of the chip or the system, verifying your SerDes is up and running, looking at your digital functionality only, go into the duct and back to the DDC, or of course, if you want to do a little bit of RF loopback. So with that, I appreciate your time today, and we'll turn it over to Michael Potter to cover the Mercury specifics. Thank you, everyone.
Well, hello, everybody. I'm Michael Potter, a senior principal firmware engineer at Mercury Systems, and I'm going to be taking you through our RFS1140 device today and some of the preliminary performance information that we've gathered. So without further ado, I'll jump right in. So first, I want to give us an overview of the RFS1140, the block diagram eval board, and the demo design that we're going to use to test the device. And then I also want to cover the test environment used to gather data. And then I'll jump into ADC performance, isolation of channels, analog response of the DDC and DUC, and then some latency numbers. So without further ado. So first, we're looking here at a block diagram of the RFS1140. As discussed earlier, it extends the Versal VC1902 with cutting-edge RF integration and SiP support integration for enhanced swap. If you're not familiar with the term SiPs, that's the processor subsystem on the Versal. It also implements this RF integration with two of the Jariet ElectroMA JTX06402 devices that Philip was discussing earlier. And the SiP support integration includes onboard LPDDR 4 gigabytes worth and onboard NOR flash 4 gigabits worth. So you can, you could have an implementation that doesn't use external memory if you so choose. Additional benefits of the RFS1140 and of Mercury Systems is that you have optimal flexibility in that we can make derivatives and custom variants of this part. The device is ruggedized to mil standard 883 with operating temperatures from minus 40 C to 85 C, so it's reliable in harsh environments. You have optional secure boot and runtime options, so data and IP protection, integration on the eval platform that I'm going to show you in a little bit with a BSP and reference design, or you can buy productized Mercury platforms. These offer you ease of development to deployment. And we also have DMEA accredited facilities for design, assembly, and test, which gives you a trusted supply chain. So if those matter to you, the RFS1140 is for you. Then let's see, next slide. So this is our evaluation board. If you look at the block diagram on the left-hand side, you'll see 4 DAC channels and 4 A to D channels, which is what we're going to focus on today. Just above that is an advanced clock circuitry box in orange with lots of different connectors, and there are lots of clock options that you can experiment with on this board. This board not only allows us to characterize and demonstrate the RF subsystem, but it also can provide a good customer prototype platform. So with that, you've got lots of options. There's a green box up at the top, which manages the power and the clock programming, a supervisor device. And as Dagan mentioned earlier, the interfaces of the VC1902 that aren't used to connect to the ElectroMAs are brought off chip. So we've hooked those up on the eval board to an SD card interface to boot out of. Of course, you have the NOR flash that's embedded in the part, so you don't have to use that. And then we have 2 external DDR4 UDIM interfaces. You also have, of course, the onboard LPDDR that's available. Those SerDes interfaces that were described earlier, 2 of them are used for 100 gigabit Ethernet, and one of them is connected to an FMC Plus connector for expansion. And with a certain adapter cable, you can make this a PCIe endpoint as well. So lots of options on the eval board. All right, so the demo design that we actually loaded, so the firmware and software that's on the device that we're using to test, architecture kind of breaks down like this. So the RFS1140 and its corresponding eval board gives us a means of doing that testing. Then we have firmware that's running in the programmable logic of the VC1902, which gives us the infrastructure to demonstrate that RF subsystem. And then we have embedded software running on the SIPs, or the processor system of the VC1902. And it includes a library of commands to set up and operate the RF subsystem and control the firmware infrastructure as well as the ElectroMAs. And then there's application software that you run on a Windows PC that talks to those commands over IP in the embedded software and gives you user-facing tools that send the commands to embedded software. So the pictures below, you can see our eval board on the left, the block diagram of the firmware design, followed by the software architecture for the embedded software, and one of the apps that controls the system from the user interface perspective. Okay, so the demo design itself on the ingress is implemented with 4 of the A to D channels. As we talked about earlier, there's 10-bit samples coming from the A to Ds, and they're in real format. The sample rate that we're implementing in the test design is 64 gigasamples per second. We're decimating by 8 with the DDC. The samples from the DDC are 12-bit complex samples, so 12 bits of I and 12 bits of Q. You get an effective IBW of 6.4 gigahertz per channel, and the analog bandwidth that we're observing and testing is 100 megahertz to 36 gigahertz. The egress side is very similar and symmetric. We have 4 DAC channels. Same thing on everything else, except instead of decimating, we're interpolating because it's an up converter. So the ingress and the egress, that's what we've implemented. And it's definitely worth pointing out that the demo design targets the operation at the highest sample rate with the lowest decimation and interpolation, which gives you the highest IBW. But it's also possible to do all kinds of different combinations and settings in the RFS1140 to give you what you might want in your solution. So sample rates could be anywhere from 40 to 64 gigasamples per second, decimation from by 8 all the way to by 1K in powers of 2. Sample widths could be 12 bits or 12 bits padded to 16 or 16 bits. And there are also fine tuners in the ElectroMA parts, and you can use up to 4 fine tuners per channel if you go to higher decimation and interpolation. So if you think about 4 channels and 4 tuners each, you could have 16 tuners operating simultaneously to pick through that very broad IBW simultaneously. In the test environment, we're going to first talk about the lab equipment. And so, of course, we had an array of Rohde and Schwartz SIG gens, one for a clock source, one for a signal source, and we had a spec-in to capture signals with, and an oscilloscope to do our latency measurement. The cabling from the equipment to the eval board included SMA cables, MMPX cables, SMA to SMB, whatever you might need to hook things up, as well as balance to go from the single-ended equipment to the differential A to D and DAC inputs. We use the Hyperlabs broadband HL9404 balun, which gets you 50 kilohertz to 40 gigahertz, as well as some inline DC blockers. And when we were measuring the latency, I put some T's in there so that I could not only operate the equipment, but look at it with the oscilloscope, some terminators when calibrating cables, and a filter bank that I put together for 100 megahertz to 4.1 gigahertz to knock down some of the harmonics that the signal generator creates when we're doing our measurements. So that gets rid of those or knocks them down a lot. As far as test environments, we do ADC testing, where we do a burst collection into the ElectroMA from a SIG gen. It then goes into the on ElectroMA diagnostic unit and pulls those samples across with SPI to the processor system, which then hands it up to the application software to be analyzed and interpreted. When we're doing ADC DDC testing, we do that same burst collection, except instead of going into that diag unit, now it goes through the DDC and that decimate by 8 that we talked about. goes across the JESD204C interface across the SerDes into the FPGA's programmable logic, into a sample processor core, and ultimately into a receive sample memory that the SIPs reads from and provides to the application software. The DAC and duct testing is quite similar, except in the reverse direction. So in that case, the application software is telling the SIPs what it wants to do, frequency-wise, tuning-wise, etc. And the sample processor plays out max amplitude samples, which drive into the DUC. And the DUC's NCO is used to tune whatever frequency you want to generate. And then the amplitude is controlled by the gain controls on the DUC and the DAC. So next is the setup that we used for the latency measurement, which is the bent pipe test environment. So the SIGGEN feeds the signal in. Again, it goes all the way through the ElectroMA, across the SerDes into the programmable logic, and the sample processor turns it around, delivers it back again into the DUC and out the DAC. And of course, we're measuring the ADC in and the DAC out and on the oscope to get our measurement. The measurement is actually on the SIGGEN. We're producing an enveloped, pulse modulated enveloped sine wave, so that there's an edge that you can track for triggering the oscope, but we'll get into that later. So now let's look at our performance numbers. So the ADC performance, in all of the numbers that I'm about to show you, the same test environment existed. Essentially, we're driving the SIGGEN at whatever amplitude is necessary to achieve -1 dB full scale at the A to D. So, as measured at the A to D. So we're turning up the amplitude on the SIGGEN to achieve that level as we increase frequency. The samples are 32K sample collections, and they're real samples because they're coming from the A to D. We calibrate with internonlinearity calibration and interleave calibration at 12 different points along the band that we're looking at. And the RF input is swept from 100 megahertz to 30.1 gigahertz in 500 megahertz steps. So, and of course, that's adjusted to the nearest bin so that it's, bin frequencies so you don't get crazy aberrations. As far as insertion loss, I did factor in the effects of the SIGGEN, the cables, the filters, the balun, the DC blockers in my numbers. So the amplitudes that you're seeing have that insertion loss adjusted for. In addition, I also used the S parameters from the eval board, insertion delay insertion loss from the connector to the device to try to factor that out. Although I think empirical measurements would be more accurate. So I don't love the S parameters here, and I'm definitely noting that this is an actual de-embedding of the actual board with real measurements. This is just the model. It also doesn't include the effects of the socket. So on my eval board, I have a socket so that I can put different parts in there and measure different guys. So so that's not factored in as well. So naturally, the performance will be better than this. Also, the filter bank was used up to the 4.1 gigahertz point. So with that, all these measurements that I'm going to describe include that sort of setting. So if we look, we can see the performance going from left to right, at 100 megahertz, and then up until you hit about 18 gigahertz, you're in this same sort of range in your analog response. Once we get to the higher frequencies, you'll see these the high frequency ripple is occurring, and we're still trying to figure out where that's coming from. It seems like that's potentially the evaluation board with some sort of resonance effect, but don't want to completely say what that is just yet. So we're trying to figure that out. And also, we only filtered the low frequencies to 4.1 gigahertz. So it's certainly possible that second Nyquist stuff is folding back in and doing strange things or something to that order. And of course, this is preliminary data. So with all those qualifiers, there's improvement to come for sure. But this is the analog response, which looks pretty good. Then we go over here to SFDR, so our spurious free dynamic range. And as you can see, we're up here in the 60 to 65 kind of dB range from 4.1 over until perhaps all the way about 20 gigahertz. There are a few little blips that drop down below 60 just a smidge, and it stays pretty well all the way across. The first little zone here I've kind of boxed, and I think this is probably related to my filter bank and not de-embedding that correctly, because there's this big sort of hop that wouldn't make sense for that to be real. So also the chart down below, this plots the frequency that we put in on the bottom axis, on the horizontal axis, and on the vertical axis you see the spur that's sort of driving the SFDR measurement number. So if you look at these numbers, you can see that these are harmonics. So for example, at the 5 gig, you're seeing 15 gig is the spur. So this is the third harmonic. And remember, I only had filters up to the 4.1 gig point. So I'm not filtering out harmonics that are quite likely coming from the SIGGEN. And so this line of red dots is the third harmonic of these frequencies, which would improve all these numbers by a little bit. Or a lot. Hard to know until I filter them out. Then you see this line, which is also a third harmonic. So for example, at 22 gig, we're seeing about 2 gig, which the third harmonic of 22 is 66. And so in the third Nyquist, you're at 64. So that folds over to 2. And so this line is the third Nyquist zone, third harmonic rolling back in, and really needs filtering as well. So all of these numbers, even though they're not bad numbers, will definitely improve once we filter. So that'll help. And then on the blue line, this is where the input frequency is the same as the spur frequency that's affecting the measurement, and that's quite likely due to phase noise from the clock source, and not a real spur. So anyway, apologies, preliminary data. So the measurements are only going to get better from here, but certainly nothing scary at this point. This is a different channel, same kind of stuff. You're seeing the third harmonic here. This is a third harmonic as well, I believe. Let's see, this is 18 gig, and it's coming in at 28. So I think in this, let's see, maybe the second harmonic is 36. So the third would be 56. Well, I'm not going to do the math off the top of my head. Anyway, that's also an alias harmonic, which same kind of thing as the other channel. So flipping back and forth, you'll see the effects are different, but these are all lines that are indicative of harmonic influence. So that means our performance numbers will be better once we put a low pass filter to stop the higher frequencies from altering it, the higher frequencies from the SIGGEN. Okay, so another issue I want to point out before we get into the other measures is if, for example, you look at the SNR, so we're looking at numbers from, say, 45 to 50 until you get out here to the 18, 20 gigahertz zone. Once you hit about 19 gigahertz to 27 gigahertz, you see this sort of drop in the performance. If you look at one of these before the drop, you'll see a normal collection where the noise floor is down here below 80 dB, looking very good. And then when you're in this zone where the pedestal exists, the noise floor rises up about 10 dB. So there's some phenomenon going there that we're still investigating. Perhaps some resonance occurring from the eval board. Perhaps the lack of filtering at high frequencies is coming back and polluting the noise floor. Just not quite sure yet. So that's going to be further investigation on that one. So with that phenomenon sort of described to you, here's our SNR numbers. And this again is at the raw A to D. So obviously your SNR numbers will get to be 6 dB better every time you decimate by 2. So you can certainly improve these with decimation, and decimation by 8 should give you 18 dB improvement on these numbers in theory. The noise pedestal thing is sort of shown here, so you can see that. But good looking SNR. Then we've got the ENOB numbers. So for a 10-bit converter, starting off in the high 7s and working your way to about 7 in the 16 to say 19 gigahertz zone, and then the pedestal thing starts altering your numbers after that. So definitely have to go figure that out. But ENOB's looking good out to there. Then we've got the noise spectral density. And I did put a note up here where, I said our target was minus 138 and gave myself 12 dB of credit for decimation, but that's incorrect. I didn't factor the decimation into that correctly. So really, this is the goal was 150, I think. And so, we're hitting those numbers up to 12, almost to 16. And then it gets a little worse after that. But these are all still very, very nice NSD numbers, especially when you combine them with the crazy big IBW that you get out of these Electra MA parts. And again, the noise floor pedestal is altering my measurements. And the scale here is just from minus 40 to minus 155. So, this is not a big hump, actually. It's just the scale of the graph. All right, and then noise figure, we go from about 20 to 30 over the frequency range of 100 to 18 gig. Then we hit the pedestal again, which alters it a little bit, and sort of tracking up to 40 dB at the 30 gig point. You might ask why I stopped at 30 gig in my measurements. In this case, we're trying to drive the minus 1 dB full scale into the A to D. And in order to do that, the signal generator has to drive enough power to push into that. And the SIGGEN I had in my lab that could go to 40 gig didn't have enough amplitude at the high frequencies to overdrive the effects of the cables and the ballons and so forth. So we stopped at 30, but I've definitely got other collections I can show you where we work just fine going above that point. So future measurements that sweep the whole range will definitely catch that. Okay, isolation numbers. So let's talk about isolation. So this first chart is the RF input to RF input isolation. So with 4 channels, we see 4 different tables. The first table is where channel 1 is the aggressor and 2, 3, and 4 are the victims. The second table, channel 2 is the aggressor, and 1, 3, and 4 are the victims, and so forth. So 3 and 4. If you can see it, the asterisks in the table, there are many of them, and those represent places where the victim signal is imperceptible. It's so far below the noise floor you don't even see it. So when you see an asterisk, it's 90 dB or less, way less. Where I have numbers, they're all very good numbers. 89, 60, 68. Sorry, hard to read. 65, 64, down to 57. At 24 gigahertz, that seems to be the worst crosstalk area frequency-wise, and we get 57 on channel 2 from channel 1, and 57 on 2 to 1, 62 from 3 to 4, and 64 from 4 to 3. That's still well above the margin of our design target. So in the 22 to 32 gigahertz frequency band, we were targeting 52 dB of isolation, and we're actually 5 dB above that. The 12 to 22 gigahertz band, we were targeting 61, and we're 3 dB above that. 100 to 12 gigahertz, we were targeting 69, and we beat that by 16 dB. In the high frequencies, we were only trying to get 38 dB of isolation, and we're actually greater than 20 dB better than that. So the isolation in the RFS1140 on the input to input was fantastic. A very, very nicely done substrate. And the illustrations here are the victim spurs at the frequency of the aggressor, and these actually highlight the 4 yellow cases. The scale of the chart, if you can't see it, is from minus 50 dB down to minus 100. So, still a spike down there in the noise kind of area. Next, we have the RF output to RF input isolation. So in this case, I'm driving the DAC of and then measuring the corresponding A to D channel. So same channel aggression to victim. And in that case, you only have one line for each, because channel 1 is where the DAC is aggressing its own A to D, and 2 is where channel 2's DAC is driving its A to D, and so forth. And what you can see is a similar kind of drop here in the 24 gigahertz zone, 24 and a half in this case, where the isolation is 65 dB, 65 dB, 66, and 74 dB. This is with the DAC channel driving the max sample into the DUC, with the max gain setting of the DUC and the DAC, and the sync filter is in bypass mode. So it's driving as hard as it can drive, and the effect is still very low, well exceeding our design targets. So again, in the 22 to 32 gigahertz range, we were targeting 50 dB. We're getting 15 dB more margin there. So very attractive isolation channel to channel. The 12 to 22, we were targeting 60. We got 6 dB of margin. The 100 to 12, 68 was our target, and we beat that by 12 dB. The 32 to 36, 44 was our target, and again, more than 20 dB of isolation above the target. So again, really nice job on the substrate of the RFS1140. Next, we look at analog response as measured at the DDC and the DUC. When I was doing the crosstalk measurements or the isolation measurements on the A to D channel, I'm driving a signal in on the SIGGEN and measuring it at the DDC. So pretty much I took those measurements and plotted them so that you can get an analog response for all 4 of the channels as it looks at the DDC. I did not de-embed any of the insertion losses from the cables, baluns, etc., like I did on those other charts, just because I wasn't sure about how they were influencing things. So this is completely without any kind of de-embedding of any of the effects of insertion loss from the equipment into the part, but you see a nice smooth performance there. And then similarly on the DUC, this is where the DAC is driving out, and I'm driving the spectrum analyzer and measuring the power at the spectrum analyzer. And again, you see a pretty smooth curve here. And again, I did not de-embed any of the other effects. So, the insertion loss here is not represented. So obviously the numbers are better once you get credit for all the insertion loss. Next, we talk about latency. As I mentioned earlier, when I was describing the test setup, we're driving into the A to D. It's going from the A to D through the DDC, across the GSD interface and SerDes into the FPGA, into the VC1902, turns around in the logic fabric in the sample processor and goes back out the SerDes back to the electro-MA, drives through the DUC and out the DAC and drives the signal. So the yellow represents the ingoing signal and the green represents the outgoing signal. And as I said, it was pulse modulated. So you see this sort of envelope of the pulse and you see the start of it here and the start of it here on the green. And the measurement of delay was 604 nanoseconds. So pretty good when you figure the algorithmic processing that Dagan was describing is in the scale of microseconds. So we're not even talking about 1 microsecond here. The latency, of course, is a function of a lot of different variables. The sample rate, the decimation factor, the interpolation, the GSD204C SerDes settings affect it. The IP on the VC1902 GSD, the extended multi-block clock period changes it pretty significantly. And so it's hard to say that this is the insertion delay the latency that you'll have in your case. This is just one empirical measurement of one scenario, and Obviously, there are ways to do the math and figure out what scenario you're going to be in and what your latency will be like. But there's the number for this case, which wasn't bad. And so that's the preliminary performance data that I was able to gather in this time frame. And of course, we're still actively working on gathering of data and resolving the trouble areas that we identified in the presentation earlier. So, I'm very confident that the performance that we're going to have once we get done with our measurements is going to be very attractive. And, we'll beat our expectations, just as we were able to do with the crosstalk numbers and the things that I can definitively measure at this point. So everything's looking good on the device, and we're selling parts now. So get your parts while they're hot. All right. So with that, here's who you can talk to if you would like further information about the RFS 1140. Jennifer Keenan, our product manager, she's definitely the person you want to talk to. And if you have more technical questions, Todd Clausen, he's our technical point of contact, and both of them are available to be reached out to with any questions you might have. And we have eval boards and parts available now. So there you go. I'll turn it back over to Jeff to bring us into questions and answers.
All right, sweet. Well, I warned you that we had a lot of content to get through in the beginning here. So thank you for sticking around here to the end of the Q&A. I want to thank all of our presenters and just give a couple reminders. And we have been answering some of the questions in the background. So I think that we got to a good amount of them, but we'll try to get to one or two before we actually close out today. So first, you'll be able to come back and watch this on demand anytime. You can use the same link that brought you here, and we'll also be sending a thank you email shortly after the close here today. And then if you could fill that survey out before you leave here today, that would be super helpful as we try to bring you the best webinars that we can. And then again, in the top, you will see a resources tab with links to learn more about what we talked about today, as well as contact anybody that we want you to keep the conversation going. And then you can find in the Documents tab a PDF copy of today's slides for your reference. Okay, so I will kind of just give it over to the presenters here. Any of these questions that you want to hit before we close here, and we'll be able to follow up offline if we don't get to your question too.
All right, Jeffrey, let me give it a shot. So I'll start with can we expect about half power consumption when using only ADC? So if you're turning off the DAC versus the ADC, maybe I'll throw that one off to Philip for Jariet power numbers.
Yeah, thanks, Michael. And it looks like it's probably going to be about a 30 to 40% saving, not half power. There is some static power. Okay, great. Next question, does higher level of decimation produce higher bandwidth words? So if you decimate more, you've got lower data rates that you need to push across the SerDes to get into the FPGA. And so you can either use that extra bandwidth to send more tuners, or send more channels, or not send it and operate the SerDes at lower data rates and save some power. So you have options. And Michael, I'll add some color to that. With respect to what kind of bit width is coming out of the digital down converter after decimation, the Electra die does set that to 16 bits regardless of decimation factor. Okay, great. Let's see. On the demo design, is the padding to 16 bits due to bit growth from the DDC duck to fit the standard IP cores in Vivado? No. So in the 64 gigasample per second range, you don't have enough bandwidth or data rate through the SerDes interface to send 16-bit samples. So you end up using 12-bit samples to fit your channels across the SerDes.
and then you have 12-bit samples that you get to expand into 16 bits with some padding on the bottom to, mathematical adjustment to fill in the LS bits. But yeah, if you operate at the higher frequency in the best or least decimation, then you need more throughput than you've got. So that's where the 12 bits comes in. If you decimate more, then you can go to the 16 bits, or you lower the sample rate, then you can get 16 bits. So there are trade-offs to be made. Okay, are Electra MA and VC1900 chiplets interconnected with AXI-bus or only SPI for configuration? So actually, the Electra MA has a really nice APB bus, which is a very wide parallel bus that can be used to configure the part. So we use some of the XPIO banks of the VC1902 to connect up not only the SPI, but also that APB bus. So you can either use SPI if you want to be small and simple, and of course, then it's slower, or you can use the very wide APB bus to do agile control. Let's see. On the clock source, are there stringent requirements on the clock source to note? Yes, certainly. You want low phase noise clocks when you're implementing products like this, or it will affect your measurements on your A to D, of course. So I don't have those specs with me. Didn't put those out in the slide deck, but those will be in our data sheet for sure for you to look at. Let's see. Can you elaborate on socket for SiP? Is it supported production mount option? So it's a high-end ironwood socket that's good for high-performing devices. But a socket is a socket, right? If I'm mounting my RFSiP or my RFS1140 to a board directly, I'm going to get better performance than I would get if I put it in a socket and go through the extra inductance and parasitic losses of a socket. So that is infecting things. I didn't mean to say infecting. I meant to say effecting things a little bit, but. That's the nature of wanting to switch out parts on one board for testing. And I think that's all the questions we have right now.
Yeah, well, thank you for the rapid fire
Yeah.
clear out of that. That was awesome.
No problem.
Cool. Well, all right, then we got to everybody's question here today. Thanks everybody for joining and sticking around there for the end of the Q&A. I think we will wrap up there. I want to thank everybody again for joining us, and we'll see you next time. Thank you very much, and have a great rest of your day.
Thank you.
Thanks, everyone.